Hi, my name is Sejaswini Patel, and I'm an business researcher and a deputy senior member. And I'm like in Texas, and I'm presenting a joint work with Sandeep and Vishwanathan. Our paper is titled as Compute Optimal Resource Allocation for Distributed Large Language Model Inference in Cloud Scale Intelligence System. And the system we introduce is called Rapid Scale. The core question we answer is how do you serve the large language model at the production scale without paying for compute you don't need. In nanoseconds, here are our headline results. Adaptive scale achieves 2.1 times better cost efficiency, 20% higher throughput, and 67.2% accuracy on GSM. It can 90% scaling efficiency on a 4 node cluster. Let me walk you through how we get there. Let me frame the problem we are solving. On the left, you see the production dilemma. A 70 billion parameter model costs roughly 1,200 per day on A100s and consume 140 gigabytes of 140 gigs of GPU memory, and yet it all delivers is 5 or 10% points more accuracy than 7 billion model, which costs just 144 per day. That's nearly an 10x cost premium for marginal accuracy gain. But the real problem isn't choosing between 7 billion and 70 billion. It's that the static allocation where large or small waste is 50 to 80% of compute. Why? Because workloads are heterogeneous. On the right, you can see what we are consistently observes across thousands of production queries. Roughly 16% are easy and can be answered with simple greedy decoding. 30% are medium difficulty, benefit from best of n sampling. Only 10% are genuinely hard and need to deep research. The key insight is the 7 billion model with intelligence adaptive search and matches and greedy 70 million model. 1/10 the memory and 1/8 the flops for per token. You don't need to bigger model. It's smarter computer allocation. That's the foundation of an adaptive scale. Adaptive scale is built on four tightly integrated components, each addressing a gap in specific gap in existing systems. And specific gap in existing systems component O1 is a difficult predictor. There's a 12 million parameter element bit to attach to frozen element encoder. It achieves 8% classification accuracy at just 1.8 millisecond P50 latency and fast enough to add negligible overhead to every request. It also had an excellent calibration with an accepted calibration error of 0.08 for 8 component. O2 is adaptive resource allocated. It uses a two-stage hung algorithm to assign request to nodes based on a predicted difficulty and current load. By decomposing the allocation problem, we reduce worst complexity of O times and O plus n cubed. We stay within 5% of the online oracle. Component O3 is a hierarchical scheduler. It represents two levels: a global scheduler that routes requests by strategy and local scheduler that batch compatible tasks together. The key innovation is strategy over batching grouping requests that uses the same test time strategy, which raises GP utilization from 67 to 84%. Component 04 is electric scaling. Adaptive scale enabling switches between a data parallel, piping parallel, hybrid topologies depending on the workload pattern. It uses a 15% reconfiguration threshold, 60 has stitched window to avoid thrashing and yielding, and 15 to 25% throughput gain per configuration event. These four components were uh, like uh, syn- synergistically. The ablation study later will show that each one independently contributes to the final result. Let's zoom in the difficulty predictor since it's more critical enabler of everything else in the adaptive scale. The table shows performance across our three evaluation benchmark. The classification accuracy ranges from 80.1% on math to 7.3% on human eval with GSM 8K in the middle of at the 84.2% precision and recall and are well balanced, and F1 score closely track accuracy, indicating the predictor isn't the simply biased towards one class. The calibration error EC is a key metric here. At 0.048 on GSM 8K, the predictor's confidence scores are closely aligned with an actual outcome. Because we use confidence threshold to route requests, a poorly calibrated predictor would either over allocate expensive compute to easy queries or under allocate on hard ones. Latency is equally important. P50 latency is under 2 millisecond across all benchmark with Alaric cache achieving 78% hit rate on repeated prompt patterns, and the effective range overhead drops below zero point 0.5 milliseconds and making the predictor effectively free at scale. One finding worth highlighting: even 84% accuracy misprediction errors are asymmetric in favorable way, misclassifying a hard query as a easy, which happens about 12% of the time. costs 1 to 2% point of accuracy, but saves compute. The reverse, the calling, the uneasy query hard-based compute but preserves accuracy. This asymmetry means adaptive allocation remains beneficial even when the prediction aren't the perfect. Um, Symmetric means adaptive allocation remains beneficial even when the predictions aren't the perfect. Now look at now. No, Now let's look at the accuracy results. The bar chart shows the five systems evaluated at GSM 8K Math and human eval using Mistral 7B on single NVIDIA 8400 GPU. Graded coding shows in gray a GPU's baseline 50 to 54.3% on GSM 8K static best of 16 DGs. 65.1% by running 16 candidates and selecting the best static best. Redo pushes to 67.8% alpha saw and strong statistical multiplexing baseline from OSDI 2023 and achieved 63.4%. Adaptive scale which is 67.2%, just 0.06% point below the best of 32, but at dramatically lower because that's 2.1% point better than best of 16. The callouts on the right tell the full story across all three benchmarks plus 2.1 pp on GSM 8K plus 3.4 pp on math plus 1.9 pp on human eval, all versus the best of 16 baseline. The bottom line adaptive scale achieves approximately best of 32 accuracy at best of 16 compute scores. It does this by routing 60% of easy queries to grid decoding and 30% of medium queries to best of n with moderate n and concentrating three searches on the top 10% of hard queries. It actually helps. Accuracy told only half of the story. Let's look at the throughput and the cost. The left chart shows throughput in requests per second at three load level. Light at 10 requests milliseconds and 50 requests per second and heavy at 100. The static best of 16 is the most concerned baseline. It achieves only 3.1 requests per second and the light load and 24.6 at heavy load because it uniformly applies expensive 16-bit sampling to every request versus very large language model baseline which is 42.7 at medium load, but rapid scale which is 51.3 at medium load and 20% improvement. 82.1 at heavy load which is a 234% improvement over the best of 16. The reason is straightforward by routing 60% of queries to greedy decoding and rapid scale free GPU capacity that would be otherwise consumed by necessary sampling. The right panel shows cost per thousand requests on A4000 price at 0.76 per hour. Grid decoding is the cheapest, $0.27 per sacrifice accuracy. The best of 16 of $0.85 for 65.1% accuracy. Adaptive scale achieves 67.2% accuracy, actually higher at just $0.52. So it's 2.1 times improvement in cost efficiency or equivalently 0.33 saved per thousand requests at higher accuracy. For organization running a million of requests per day, this translates to a substantial infrastructure saving. So, so these are the result. This is the ablation study. Ablation study on a lab systematically removes one component at a time, starting from full adaptive scale at 67.2% accuracy. Removing the difficult predictor drops accuracy to 65.1. Removing adaptive batch costs less in accuracy, but still drops throughput by 46.2% requests per second. Removing strategy selection, forcing all queries through one strategy regardless of difficulty. The scalability chart on the right side shows our simulated four node cluster results going from one node at 82 point like one node at 82.1 and like this like our two node at 156.8. Uh, at a four node, we achieve 294.3 requests per second again. The idle of 328.4. That's a 90% scaling efficiency. The linear scaling is possible because the best of n sampling is embarrassingly parallel. Each candidates can be generated independently across nodes with minimal cross-node communication for results and aggregation. Uh, I want to give you an honest assessment of adaptive scale works best and where it doesn't. On the left, the green panel shows ideal deployment conditions. Heterogeneous difficulty. Adaptive scale delivers maximum value when your workload has heterogeneous difficulty. 60-30-10 split we observe across math code and factual QA domains. If you're serving Mistral 7B class model for customer-facing reasoning tasks, where most queries are routine but a meaningful minority need deep research, Adaptive Scale is designed exactly for you. It is also suit batch analytics and offline evaluation, where variable latency is acceptable and cost-conscious production deployments in predictive domains. On the right panel shows where Adaptive Scale provides a limited benefit. If your workload is uniformly hard, all prompts genuinely need 32 or more candidates, there is no routing in because everything goes to the expensive path anyway. Similarly, if P95 latency targets under 100 milliseconds, 2 milliseconds prediction overhead, 3 to 5 milliseconds routing delay become non-trivial. Two other limitations worth flagging: repeatedly shifting domain costs per crystal. Accuracy can drop 60. Um, Zero shot on new tasks like medical or legal. Multimodal input reduce reliability since we estimate difficult from text feature alone. So, multimodal, rapidly shifting domains. All those cases, static, best of n baseline or larger model may be more appropriate. We believe in reporting limitations. So adaptive scale makes, let me close the summary. Um, Let me go to summary for contribution and what this means for community. Adaptive scale makes four technical contributions. First, we prove that the distributed test time allocation problem is NP hardware reduction from multi-knapsack, and we provide 1 minute approximation and guarantee under the large language population regime. And second, our 12 million parameter difficulty predictor achieves 84% accuracy under 2 milliseconds. So these are these are total four things. Um, NP hardness proof, difficulty predictor, hierarchical scheduler, and elasticity dip. So these are all the contributions that we have done as part of this paper. And this is our conclusion. Adaptive scale is the first framework to tackle the intersection, test time, compute scaling, and distributed serving, and intersection that prior work like LLM, DServe, and Alpha is not addressed by routing 60% of easy requests to greedy decoding and concentrating expensive compute on 10% that need it. We reduce the cost from 0.85 to 0.52 per thousand requests while simultaneously improving the accuracy. So thank you for providing an opportunity to present here. I am a primary author of this paper, Tejas Praveen Patel, and this is my email. For any queries, definitely reach out to me over this email. And thank you so much for giving me opportunity to present.